I want to tell you about something that happened just a few days ago that genuinely stopped me in my tracks. A small startup called Elon Systems quietly dropped what might be one of the most significant neuroscience announcements in years, and the tech world, for the most part, barely blinked. But I think this one matters a lot. Elon Systems took the complete brain of a fruit fly, every single neuron, every single connection, and made it digital. Then they hooked that digital brain up to a virtual fly body, ran the simulation, and watched what happened. The fly walked, it groomed itself, it fed, and here's the part that should make you sit up. Nobody programmed it to do any of that. There was no training data, no reinforcement learning, no reward signals, just a biological brain copied neuron by neuron reconnected to a body, doing what brains do. That's not AI in any traditional sense. That's something else entirely. Now, to really understand why this is a big deal, you need to know what a connectome is. Think of it like a wiring diagram for a brain. Every neuron is a node, and every synapse, every connection between neurons, is a wire. The connectome maps all of it, every single one. For the fruit fly, the mapping was completed in 2024 by an international research consortium called Flywire. It was a 10-year effort. Scientists took 7,000 ultra-thin slices of an adult female fly's brain, imaged every slice with electron microscopy, and then used AI to identify and connect all the neurons. The result was a complete map of over 125,000 neurons and 50 million synaptic connections, published in Nature, open to the public. Now, the fly brain might sound trivial. It's tiny, but it's not simple. It has circuits for vision, smell, movement, learning, and even some forms of social behavior. It processes sensory input and generates coordinated motor output. It's a real functioning brain, just at a scale we can actually work with right now. Now, before Flywire, the most complete connectome we had was a roundworm called C. elegans. All 302 neurons of it. OpenWorm, a project that digitalized that worm, was already considered impressive. Elon's fruit fly is a 400 times jump in neuron count from there, so this is not a small step forward. Now, here's where it gets interesting. Elon Systems, a San Francisco-based startup co-founded by physicist Dr. Alex Wisner-Gross, who comes from Harvard and MIT, took the Flywire connectome and did something nobody had done before. They didn't study it. They didn't run statistical analysis on it. They ran it. They implemented the entire neural blueprint inside a computer simulation. Every neuron, every connection, every synapse weight. Live in software. That simulation is what they call a brain emulation, not a model trained on brain data, not a neural network inspired by biology, an actual copy. Then they connected that emulated brain into a virtual fly body. For the body, they used a NeuromechFly V2, a biomechanical model of the fly built from the actual X-ray microtomography scan of a real fly. It has 87 independent joints and runs on MuJoCo, the same physics engine used by the DeepMind and OpenAI for robotic research. The virtual body is physically simulated. Gravity, forces, contact, all of it. The brain and body sync every 15 milliseconds. Sensory events and the virtual world activate the right sensory neurons. The brain processes them. Motor outputs go to the body. The body moves. That movement changes the sensory state, which feeds back into the brain. It's a closed loop. A real sensory motor loop running in a computer, and it works. In 2024, when the brain model was published by Nature, it predicted motor behavior with 95% accuracy on disembodied tests. Now, embodied, it produces naturalistic walk, grooming, and feeding behaviors without a single line of explicit behavioral programming. Now, I think the most important thing to understand here is the philosophical gap between what Elon is doing and what OpenAI, Google, and everyone else in the mainstream AI space is doing right now. ChatGPT, Gemini, Claude, all of them are trained on massive datasets. They learn by exposure. Reinforcement learning systems, like the ones that play Go or control robots, learn by trial and error. These are all forms of learning from data. They are systems designed to imitate imitate patterns. Eon's approach throws all of that away. There is no learning phase, there is no training data. The fly brain emulation didn't get better at walking over millions of iterations, it just walked, because the biological wiring that makes a fly walk was copied faithfully into the simulation. The behavior isn't learned, it's inherited from the structure of the brain itself. This is the difference between studying how birds fly to build an airplane versus actually copying the biological machinery of the bird. One produces something that works like the thing you studied, the other produces a copy of the thing itself. The implications of that distinction are enormous, because if you don't need to train a system to behave intelligently, and if you just need to copy the biological structure that already produces intelligent behavior, then the path to general intelligence isn't about bigger datasets or smarter architectures, it's about better brain scanning and better simulation. Now here's Eon's roadmap, and I'm going to be honest with you, the first time I read it, I thought it sounded overly ambitious, but the more I dug in, the more I think they actually have a case. The fruit fly has 125,000 neurons. Within 2 years, Eon plans to attempt a mouse brain emulation, which is roughly 70 million neurons, which is 560 times the fly's count. They are already collecting the data needed to do it, using expansion microscopy to map every neural connection and running tens of thousands of hours of calcium and voltage imaging to capture how those networks actually activate in living tissue. The key argument from Eon's team is that scaling up is primarily an engineering challenge, not a fundamental scientific one. The methodology, map the connectome, emulate the neurons, simulate the body, is the same at any scale. It just requires more compute, more scanning resolution, and more data, and all three of those things are improving fast. Specialized neuromorphic chips designed for a neural simulation are becoming more capable. Brain scanning technology is advancing. Storage and compute costs keep falling. From mouse, the destination is obvious. If you can emulate a mouse brain, you are one more order of magnitude from something far more significant. Robin Hanson, the economist and theorist behind the concept of whole brain emulation, is an advisor to Eon. That's not a coincidence. These people are thinking seriously about the long-term gain. Now, is this going to happen next year? No. Is it going to happen in the next decade? That's a more interesting question. I think the honest answer is maybe, and that maybe carries a lot of weight. Now, I'll be straightforward with you about where I stand on this. I think this is genuinely one of the most exciting things happening in science right now, and it's flying under the radar because it doesn't fit the familiar narrative of AI progress. There's no benchmark to report, no chatbot to demo, no product launch, just a tiny simulated fly walking around a physics engine doing things that no one told it to. But that quiet quality is exactly what makes it so interesting to me. The big AI labs are competing on scale, more parameters, more data, more compute thrown on fundamentally the same paradigm. Eon is doing something structurally different. They're not building intelligence from scratch, they're copying it, and copying something that already works is a very different engineering problem than inventing something new. Now, what I find most compelling is the scientific rigor behind it. This isn't a startup making wild claims without peer review. The foundational brain model was published in Nature in 2024. The connectome data is publicly available. The body simulation uses established physics engines. The approach is reproducible and grounded in real biological data. Now, does this mean we're about to have digital human brains running around in simulations? No. There are enormous challenges between a fly and a human, not just in scale, but in the sheer complexity of mammalian neural dynamics. Eon themselves are careful to note that the current fly emulation is a research platform, not a proof that structure alone is sufficient to recover every behavior. But the proof of concept is here. A complete biological brain has been emulated, connected to a simulated body, and produced naturalistic behavior without training. That threshold has now been crossed. Everything after this is a question of scale, and in technology, questions of scale tend to get answered faster than anyone expects. Keep your eye on Eon Systems. I genuinely think this is one of the stories we'll be looking back on in 20 years as a turning point. The moment the path to AGI started looking less like a machine learning problem and more like a biology problem.